Hi, welcome to another Algebra 1 video. In this video we're looking at section 3.6, which is linear function transformations. In this video we will learn about the translation of linear functions. Before we talk about the types of transformations, let's first look at the parent function and the general concept of transformations. We're all familiar with many types of linear functions. You could come up with a linear function where y is defined as 2x. You could also come up with y equals to negative x plus 1, or you could come up with y equals to 1. And if we graph these functions, you get different types of lines with different orientation or slope. So if we look at y equals to 2x, you get a line that passes through the origin, but it's steep. If you look at y equals to negative x plus 1, the slope is in the reverse direction, but this time you're not passing through the origin. Instead, your y-intercept is 1. In this case, you have a flat line, so you have no slope. And for this flat line, you're crossing the y-axis with the y-intercept of 0, 1. But if we look at all these functions, we can see that they're not the simplest form of a linear function. For linear functions, we know that the most common form of writing linear functions is the slope-intercept form, which is y equals to mx plus b, where m is a coefficient of x, which is also the slope of the line, and b marks your y-intercept. If we look at this graph, we have a coefficient of negative 1, so here we have a slope, and we're also adding a constant b, which is 1 in this case. So this function is not the simplest form of a linear function. If we look at this one, we have no slope because this is like saying y equals to 0x plus 1. So our slope is 0, but we still have that 1 which is added, and we don't want that b. If you look in this case, we don't have the b, so here it's plus 0. But we still have that coefficient of 2, which is the slope of this line. So by looking at these lines and the functions that represent them, what do you think is the simplest form or the parent function of linear functions, while also maintaining a relationship between y and x? Well, that simplest function or the parent function for a linear function is y equals to x. Y equals to x is the simplest form because it consists of the two variables that we require, and it has no additional constants like the b from y equals to mx plus b. And if we look at this function more, we can see that there's no coefficient. There's only a coefficient of 1, which is negligible, so it's the simplest form we can get. And if you graph the line y equals to x on a coordinate plane, you get a line that passes right through the origin. So its y-intercept is 0 and its x-intercept is also 0. And this line has a slope of 1, so we're not adjusting the steepness of the line to make it steeper or less steep. And we're also not shifting that line along the y-axis or the x-axis. So the line y equals to x is the parent function of all linear functions, whereas these lines that you get are all just transformations of the original parent function y equals to x. The concept of transformation just means to change the orientation or the shape or the size of this line so that this line can look like these two lines. And at Algebra 1 level of transformations, for linear functions you'll most likely come up with translations, reflections, or stretching and shrinking of lines. So let's begin talking about the first transformation, which is the translation of lines. Translating a line simply means to move a function's position. By shifting a parent function up, down, right, or left, you can translate the function. We know that the parent function for all linear functions is y equals to x. And if we graph the parent function, we get something that looks like this. The line passes through the origin of 0, and the line has a slope of 1. On this first coordinate plane, let's translate this line y equals to x upwards and downwards. So if I shift this line y equals to x from the origin to 1 unit upwards along the y-axis, then I get a line that looks something like this. So I've translated the line y equals to x, which crossed the y-axis at the y-intercept of 0, 0. But then when I translated this line upwards by 1 unit, my new y-intercept is at this point, and this point is 0, 1. So all my y values on this red line have been increased by a quantity of 1 for every y value on the original green graph. Now let's do a vertical shift downwards by a quantity of 1. And if you do that, you get something that looks like this. So in this case, I've shifted my green graph, the original parent function y equals to x, downwards by 1 unit. And by doing so, I've also shifted my y-intercept, which would be 0, negative 1. So all my y values for this new red line have been decreased by 1 for every y value on the original parent function. So first I translated the original parent function y equals to x by 1 unit upwards, and now I've done a vertical shift downwards by 1 unit. Now let's look at the second coordinate plane, where I've also graphed the function y equals to x, and instead of translating it upwards or downwards, let's translate it leftwards or rightwards along the x-axis. So if you translate the function y equals to x to the right by 1 unit, then you get a function that looks something like this. So in this line we can see that the difference is I've moved along the x-axis and not the y-axis, and I've also moved towards the right by 1 unit. And we've also changed our original x-intercept of 0, 0 to 1, 0 for the red line. In this translation towards the right, all my y values have remained the same, except all the x values have increased by 1 value. So we went from 0, 0 to 1, 0, but our y value is still the same, which is 0 and 0. So this is a horizontal shift to the right by 1 unit. Now let's translate the parent function y equals to x to the left by 1 unit. And if you translate it, you get a graph that looks something like this. So this time all my x values have been translated to the left by 1 unit. So in this case, our y-intercept has shifted from 0, 0 to the new x-intercept of -1, 0. This means that all my x values from the original parent function y equals to x have been translated to the left by 1 unit, but all of my y values from the original parent function have remained the same. So here I subtracted -1 from the x because we translated to the left by 1, but our y value is still the same. We have 0, 0 here, and our y value is still 0 here. So this transformation is a horizontal shift to the left by 1 unit. Now let's look at translation transformations in terms of equations. We know that our parent function y equals to x can also be written as f of x equals to x. We know that every other function that you get is a translation of the original function, the parent function f of x equals to x. So if you were to do a vertical translation of the original function f of x equals to x, you'd have to add a constant to the function f of x. So let's say that your new transformed function was g of x, and the vertical translation of g of x would be given by the original function f of x plus a constant k, which could be any number. And if that k constant is greater than 0, then you're translating the function upwards. But if it's less than 0, then you're translating it downwards. In a vertical translation, you're only changing the y values for the original function f of x. That's because you're adding something to the original function f of x, which is also your y. Now for horizontal translation, let's say that you do a horizontal transformation for a transformed function of h of x. And the horizontally transformed function of h of x can be represented as the original function. However, your x values have been translated horizontally with some -h values. In this case, note that we're only affecting the x value as we add that -h to x. However, the outside function is still the same, whereas in the vertical translation, you're affecting the whole function f, which is also your y, by adding some value k. Now let's look at some equations for the translation of the original function. In number 1, we're given that the new transformed function g of x is f of x plus 2. So in this case, I can see that I'm adding a constant to the original function f of x. I know that f of x represents my vertical factor, so this means that I'm adding 2 to the y values of f of x. And since I know that f of x equals to x, I can replace this f of x for x, so I can rewrite my g of x function like x plus 2. So this x plus 2, which is affecting this x that we had originally, tells me that I'm doing a vertical shift upwards by a value of 2. In the second question, we're given the transformed function of h of x, which equals to f of x plus 2 minus 5. So in this case, we have a compound transformation because we're not only shifting the x values of the original function f in this x plus 2, we're also shifting the whole f of x function by -5 in the vertical direction. So in this case, I know that my k constant would be -5 as we're shifting the function downwards by a value of 5. And the second part of this transformation, f of x plus 2, tells me that this is a horizontal translation. However, we're not shifting 2 units to the right, because we know that the original format for the horizontal transformation is f of x minus h. So we can rewrite this f of x plus 2 as f of x minus times minus 2. And so our actual h value is -2, and we know that if h is less than 0, which in this case it is because -2 is less than 0, then our function will be translated to the leftwards direction. And in this case, our f of x is f of x plus 2, which is also f of x minus minus 2. So I can rewrite this whole function h of x as x minus -2 minus 5. So in simplified terms, h of x equals to x minus -2 minus 5. So in this case, my transformation would be a horizontal shift of the original function f of x leftwards by a value of 2. And we've also done a vertical shift downwards by a value of 5 because of that -5, which is our k. And this is it for section 3.6 part 1. I hope you now understand the concept of the parent function and the basic concept of transformations and also the translations that we did. The other parts of section 3.6 will be linked in the description, so make sure to check them out if you want to continue learning about reflections and stretching and shrinking of linear functions. Leave a like if you found this video helpful and subscribe for more videos in the future, and I'll see you in the next video. Thanks for watching.